I'd like to welcome everybody to NASA's Guided Space Flight Center. We're holding this special briefing today to discuss the largest fragment of Comet Shoemaker leaving to strike Jupiter so far. That fragment, fragment G, struck the planet early this morning and has produced some pretty exciting results. With us here are Gene Shoemaker, co-discoverer of the comet, and with him Heidi Hamill of MIT. Gene?
Thanks, Mike. We're really here to hear from Heidi, who's got some spectacular stuff to show you. I should just remind you that Heidi is the principal investigator, the leader of the imaging team on Hubble for these observations. So she's reporting for the team for these very exciting results.
Thanks, Gene. It was just 12 hours ago that G hit, so we've been working very hard in the last half day to be able to bring you these images. And I'm sure that in a few days we'll have a lot more to show you. Right now we just have black and white pictures, no color, just hang on. So I'll just cut straight to it and show you some of the images. We were lucky enough to be observing right when this thing happened. We have one image before this sequence which shows nothing. Then you can see a tiny tip of the fireball. And just a few minutes later, 5 minutes later, the plume is growing. 3 minutes later, it's grown even larger. 3 minutes after that, it seems to have stabilized, reached peak altitude, but started to spread. And then we have a 7-minute gap, and you can see that it's completely flattened out into that pancake again. We have about 3 or 4 more images all showing that flat pancake just hanging in there, and then we start to see it rotate onto the disk. We then, an hour and a half later, took a series of images with this impact site rotated onto the disk, and I'd like to show you that particular view right now. We were using the planetary camera, and we can't fit the whole image of Jupiter in the planetary camera because it's a very high resolution camera. You can clearly see the impact site. Now, remember a few days ago I showed you a picture with a box, and I said the box was the size, 2 Earth diameters? Let me give you a sense of scale here. You can see a little bright ring, and if you could keep the graphic up so people can see it at the other places, there's a bright spot, and there's a little dark ring you can see around the spot. And then you see a larger sort of smudge to the south. That little dark ring is 80% of the size of the Earth. That large ring, that big smudge, you could easily fit the Earth inside that diameter. This is one big impact site. It looks a little oval because we're very far south and we're also close to the edge of Jupiter, so you have an interesting projection effect. Let me show you a blow-up of that. This is a blow-up in the green wavelength, and then you can see more clearly that ring I was talking about. Now, when we project that out as to what it would look like if we were looking straight on, that ring is perfectly circular. And so is that larger white ring around it. You see that little spot to the side? That's the D impact site. That went in a couple days earlier. And so G just barely missed hitting D. And I'll get back to that effect later on. Something very interesting that you might be able to see in these graphics is that as before, there's sort of a streak. There's the center of the ring and then a smudge off to the side, very black sort of thing. If you look very carefully now in that smudge around to the south, you might see rays. You see those rays? Okay? If you look very carefully, you will notice that those rays do not appear to point to the center of the ring. They appear to point towards where that smudge intersects the ring. That's very interesting. Let's show the next image. This is a green image. The following image you see is the methane band image, which I've shown you before. Remember I talked about green visible wavelengths, it's dark. In the methane band image, it's bright. And there you can see this even more clearly. You see those rays that are emanating from that intersection of the bright ring and that central streak. We don't know quite what this means yet, but I have a theory, and I'm sure everybody has theories, but since I'm here in front of you, I'll tell you my theory, and then Gene can tell you his theory. My theory is this, that the lower southern portion of that streak is the impact site itself, and that what happens is this thing streaks in there. Keep the graphic up so people can visualize what I'm saying here, either color. It goes into the lower part and streaks down into the atmosphere, and at some point it explodes. And that bright circular ring is centered on the impact site. Right? Then the fireball portions of the fireball move back out the impact site and spew out when they get to the top, to the hole. And that's why those rays are centered on the end and not on the center of the ring. Now, I'll remind you, this is just my theory, and I'm not a theorist. I'm an observational astronomer, but that's what the observations sure look like to me. Now, the question is, why is that whole streak bright? And that could very well be that that whole tube is just very, very, very hot, and it's ionized. And Jean might tell you later that all of it's rising, but that some of it spews out the end there. So that's my personal theory about what that image shows, but we're going to have to do a lot of work before we can say for sure that's what's really happening. The energy of this event was probably about 25 times larger than that first impact we showed you, and that jives very well with the sizes of these things. This is a much larger splotch on Jupiter, and very likely this splotch will be spreading out as the days go by. One interesting thing that I don't have a graphic to show you, but I'll share with you, is in one of our wavelengths, we can tell that this material is very, very thin, that big brown smudge, the black eye on Jupiter, as it were. That smudge is very thin because we can see the bands of Jupiter right through it. It's just laying right over top of that. So I think that's about all I have to say right now. We're going to be working very hard over the next few days to analyze these data. And I should add that we are not the only observatory in the world watching this. Many observatories around the country have been focused on this and are reporting very exciting results in the infrared. They've been studying that plume in the infrared. They're seeing the spot in the infrared. All over the world, people are tracking this. And
Okay, thanks, Heidi. I wonder if you want to mention the actual height, the maximum height that we see above the limb there. I don't think you gave that number.
That's a good thing to mention. In that plume, when we saw where it peaked out at some level, looks like we were seeing that about 2,200 kilometers above the limb of Jupiter. And I'll remind you that the impact sequence we showed whenever it was, yesterday, there you go. That only got about a little over 1,000 kilometers. So this is a factor of 2 higher.
Okay, great. I'd like to make Heidi mentioned the energies, and we sort of had a top-of-the-head estimate of the energy this morning, which I hadn't had a chance to actually calculate out. I'd like to make a correction for everybody because I was multiplying by the wrong number to begin with. It doesn't change our estimates of the sizes of the objects or the energy in ergs, but it is a change if you want to put it into megatons. So our best estimate, or my best estimate for the energy for G is not the 250 million megatons we mentioned this morning, but it's 6 million megatons. That's still a lot of megatons, but please make that correction. And correspondingly for A, the real number should be about 225,000 megatons. That's still a lot of megatons. But that's just a slip in a ballpark estimate I made earlier. So please correct those numbers, if you will. Mike, we'll turn it back to you.
Okay, we'll take questions now and later see if there are questions from any other NASA centers. Please wait for the mic and state your name and affiliation, please.
Bob Cook, Newsday. You mentioned there might be you're going to talk something about the interaction between G and D, perhaps?
That's great. Actually, that was a teaser, so someone had asked me this question because I have something that I want to talk about that's even more exciting. And that is, some of you have heard about the Q impact. Q used to be the brightest one before G took over. And when we were doing our planning sequences early on, we were planning on Q as our primary target, not G. Well, when Q goes in, and I don't remember the time, the date, sometime tomorrow or the next day, a very interesting thing is going to happen. Q is going to go in, And exactly 1 Jovian rotation later, 10 hours, R is going to hit right next to the very same longitude as Q. And 1 Jovian rotation after that, S is going to hit the same longitude on Jupiter. So you're going to have 3, boom, 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 right on the very, very small range of longitude. And that is going to make one heck of a mess. So we're really looking forward to that. That's well, not messes, but we're looking forward to some really interesting chemistry, because what that means is, you know, you're not just taking the atmosphere and stirring it up a little bit, you're really stirring the atmosphere up a lot. So that'll be very interesting, and that's why I mentioned the proximity of those 2 impact sites.
Bill?
Bill Harwood, CBS, for 2 quick ones. One, the very clearly defined ring around the central thing.
Great question.
That's awfully sharply defined. And the other one is, if you can see the cloud bands below the smudge, you're seeing through it, I suppose. Is there no wind at all at the altitude these things are, or would you expect that to change pretty rapidly if it's that thin?
All right, great question. That ring, there are some theorists who would love to believe that that ring is an atmospheric wave. It's too small to be a seismic wave, but it could be one of these atmospheric waves that many theorists have been predicting, Andy Ingersoll and Tim Dowling and Joe Harrington. They would love to believe that. Now, if that ring expands, then we'll believe it's a wave. If that ring does not expand, with time I'm talking about, if it does not expand with time, then we have to go back to the drawing board. We're waiting to get the next sequence of images down so that we see what happens to that ring. So it may be a wave, it may not, time will tell. The other question was about the wind's speed. This image was only taken an hour and a half after the impact, so in an hour and a half the winds aren't strong enough to perturb it on the scales that we're seeing here. Certainly over the next few days we will be watching all that material very closely to see how the winds distribute it. And it will be distributed, there's no question.
Heidi, do you want to mention that it looks as though some of the material in the spot from the A impact is being smeared out?
That's a good point, Gene. Yeah, it does look like that in some of our recent images. The A impact site is not as crisp and sharp as it once was. It looks kind of messy.
So as that material gets followed, in fact, it'll be a very nice tracer for the velocities of these upper atmosphere winds, for which there actually is no previous information. So very important information about Jupiter will come out from that.
Thanks.
Take a question over here.
Yeah, I have 2 questions. One, can you estimate the distance between that D impact site and the new one, the G one? And also, this morning John Clark showed us UV images that showed that these impact sites, when imaged in the UV, are much bigger than they are visually. Do you suspect the same is true of this, and that it is in fact even larger, the area of disturbances in UV?
I'll answer the second part first. We'll wait and see when we get some UV images for sure. It sure looked like that from the other 3 impact sites, so probably yes. Probably it will be larger in the UV. And what was the first question?
What's the separation between?
Yeah, can we do that? Yes, we can. Have we done it? Not yet. We'll get to it. Maybe they've done it already by the time I was coming out here.
We'll take a question back here.
Hi, John Rutherford with NBC. Can you talk about what kind of impact this would have on Earth if these things were hitting Earth instead of Jupiter?
Well, I told Gene I'd get him up here to answer that question. Well, let me just point out again the scale. Remember that the Earth is, about the size of that ring you saw, all right? So the scale, the physical scale of this effect is terrestrial. It's that big. I wouldn't want to be on Earth if one of these pieces landed on Earth.
If you were going to ask what's the size crater this would make on the Earth, if we're right about our estimate of the size and the energy, if it hit a continent, it would make a 60-kilometer diameter crater, thereabouts.
Well, how does that compare to the size of a state, for example, Rhode Island?
Oh, it's about 40. Well, it would pretty well, the crater would pretty well cover Rhode Island, yes. And the other thing is, if you look at the size of the material that's actually spread out, and remember that's now gone up very high, that would just go out ballistically all over the Earth. It's enveloped the Earth.
Completely enveloped the Earth.
It's gone all over the Earth, so that the material that's blown out of that crater would essentially blanket the Earth with a layer of fine debris that would just block sunlight. It would just get dark all over the Earth.
Right over here.
This is Mark Carreau, the Houston Chronicle. Regarding the sequence of 3 that happen every 12 hours later in the week, is it possible to be a little more descriptive about how close those would be together and in some, you said the same latitude, but I didn't know whether you meant the same quarter of the planet or stretched, 1/3 of the way around.
Okay, it's every 10 hours. It's every Jovian rotation. And I wish I brought the numbers with me. They're very close in longitude on Jupiter. All of these are close in latitude. They're all in the same band around the planet. What's striking about that group of 3 coming up is that they're all close in longitude. And I can't remember the number off the top of my head. I think it might be within 10 degrees. Certainly, if they have sizes comparable to, say, A or C or E, which we saw earlier this morning, all those regions will overlap.
Okay, we've got a question right over here.
Deborah Zabranko at Reuters. This is a really elementary question, but my editors have been asking, and I haven't come up with a good response. I need to make clear to our readers the difference in size between Earth and Jupiter. How many more times bigger is Jupiter than Earth?
Well, I like to put it in terms of the great red spot, the storm you see on Jupiter. You're familiar with the red spot? You could fit 2 Earths, there it is. You could fit 2 Earths inside that red spot. How many do you know the number?
The diameter is about 12 times greater for Jupiter. 12 Earth diameters, roughly.
Paul?
Yeah, Paul Racer of AP. In Jupiter's black eye there, the pupil of it, there is a white spot I noticed in the earlier pictures. Do you have any idea what that white spot is? Is that an artifact, or is that real?
I'd have to see the graphic to know exactly what you're talking about. So.
See that right above the pupil there?
I would guess that's just a cosmic ray. That's an instrumental effect in the detector. It's not a real white. It's not a white spot.
Okay.
I'll look at it. We didn't have time to really clean these images in the last 10 hours.
And I want to make very sure I understand the comparative sizes here. In effect, this is 3 concentric rings. You got a dark element in the very center, then you got a very nearly perfect ring around it, and then you got the smudge on the outside.
Right.
The Earth is the size of what exactly of those 3?
Okay, I'll give you some numbers to chew on here.
Well, can you just compare it to that?
Yeah, well, yeah. The Earth is a little bit larger than the black ring, the sharp black ring. The Earth is a little bit larger than the sharp black ring, but the Earth is smaller than the whole smudge area. Okay?
On the far end right over here.
David Chandler from the Boston Globe. I know when these images first came in Saturday night, you were surprised to see black smudges rather than white smudges, and I don't know if I've missed something in between, but what's your best thinking at this point about why these smudges are black?
I think the theories are numerous. Many people are theorizing that a lot of what we're seeing is some cometary material. Comets are very dark. And it also might be material from Jupiter that's deeper down that we're not used to seeing higher up, and that material could very well be a very different color. I don't have a very good answer for that question right now. I think I was surprised because most of the fresh features that we see on these outer planets that I'm aware of tend to be white and bright, and so that's why I expected them to be that color, and I was very surprised.
In the plume picture that you showed today, and as well as on the earlier plume pictures, you see a bright plume and then there's a dark region before the limb of the planet. Why is there that dark region between the plume and the planet?
There's 2 reasons there's a dark region there. The first is that we're seeing the crescent of the shadow of Jupiter. Jupiter is not fully illuminated, okay? The sun is a little bit off to an angle, about 10 degrees, so there's a little tiny sliver that's unilluminated, just like we see the moon in the sky has pieces that aren't always illuminated. That's part of it, but the other part is that these plumes are so high that the shadow of Jupiter, just a little sliver of the shadow of Jupiter itself, is preventing the sunlight from reaching that. And we're doing some calculations right now to tell you very precise heights of these things. We're working on it right now. But most of that is the limb of the planet. A good way to look is the bottom image. If you could put the graphic up, the bottom image, you see the edge of Jupiter, and then you see that smear, the pancake. That pancake is sitting on the planet. Okay, that pancake's not floating in outer space. The pancake is in the atmosphere, and that thin little strip there, that is that's the unilluminated part of Jupiter.
Question over here.
Yes, Jan Smith with Fox Television. In revising this morning's estimate of the power of the explosion, how do you now compare it to the size of the world's bomb arsenal?
Okay. Putting it in megatons, I didn't really change my estimate of the energy. I just made an error in converting it to megatons. And I guess we have a little disagreement. The number I've always used as the world's arsenal is 10,000 megatons. But there are other numbers floating around, and I guess the real number is still a state secret. So I've used what's been commonly used in some of the literature at 10,000 megatons. So if you compare that with the energy for our estimate of nucleus A energy is about 20 times that. Now I've heard bandied about just in this room in the last half hour a much higher figure for the nuclear arsenal, something like about 80,000 megatons. So then it would only be about a factor of 3 higher. When you get to 6 million megatons, that's a whole lot higher. And that's getting in the ballpark of 400 or 500 times what I think is a more conventional published estimate of the world's nuclear arsenal.
Okay, we've got a question right here.
Chris Leach, NHK. What was the actual size of the fragment, and also what was the time that the fragment actually impacted into Jupiter?
Those are two questions for which we would very much like to have the answers to. The time between, well, the time of that first image that I showed you with the tiny tip of the plume was sticking over, that was 7:33. That probably happened, that image probably occurred within, say, 5 minutes of the impact itself.
I would guess there's probably only a delay of a couple of minutes.
Right,
there.
so 7:33 minus 5 minutes, somewhere in that time period is when the impact occurred. And I can't remember the other question again. We still don't know the sizes of these fragments. I think if Hal were here, he'd probably say that this was 3-kilometer body.
I would say the height of the plume now, based on the modeling that we've done for a 1-kilometer impactor, is consistent with that. In other words, you know, that estimate by Hal Weaver of 3 kilometers looks pretty golden to me.
Universal time, right. At Eastern Daylight Time, that was
Subtract 4 hours.
yeah, early in the morning, very early.
Okay, can we take a question in the far corner in the back there, please?
Jim Reston for Esquire. I have 2 questions. If you could see the full plume without the shadow, would it mimic the fireball of Hiroshima?
We don't think so, no. What happens in this case is that the plume is erupting from substantial depth, and so there is a column that goes down below the cloud tops that you don't see. But what we see at the surface is just this big bump that comes up initially. Now, as it flattens out, it will kind of get kind of mushroomy out at the edges, so that there is a gap between the bottom of that and the ammonia cloud deck. And you can really, in fact, you could I think you could actually see that. It's very high. That pancake's very high up, as you saw in that last frame.
And you've also, we noticed that the plume was somewhat asymmetric, and I think that's because this is a directional thing. This thing, the comet pieces are not coming straight down onto the atmosphere. They're coming in at some angle. And so in that sense, it's a very different kind of morphology, different shape. And also, in the little scenario I sketched for you earlier, the plume doesn't really necessarily rise straight up. It might come out that
Some
tube.
of it blows out
Some of
sideways.
it blows out sideways, maybe.
The second question is, when these three fragments hit in the same location, Q, R, and S, does that increase the chances of a cyclone effect or an anticyclone that could be permanent?
I'll tell you the answer to that in about 2 or 3 days after it happens.
It does increase it, or it has no effect?
I really can't even speculate at this point. None of this stuff is something that we had expected to really see. So we're moving well into the realm of speculation. Certainly it's going to disturb the atmosphere a lot more than a single impact on one site would. I won't go much further than that, though.
Okay, we've got time for one more question before we go to the Jet Propulsion Laboratory. We'll take a question from right here.
An automotive Kyoto News Service. I heard that Japanese radio astronomers reported that they had seen something which indicates that the fragment broke into 2 pieces before impact. And I'm wondering whether the irregular shape has something to do with that. Would you comment on that?
I saw a report on the internet about some unusual radio signals, and all I can say to that is that the signature of this impact, the G, is very, very similar to that seen for A, C, and E, the ones that we have good images of so far. Does not appear to be anything other than a solid single main body or explosion or rubble pile. It seems to be only one. I wanted to make sure to mention that other site nearby to make sure that you understood that that was an old impact site, that it was not related to G. So it doesn't look like a double one from these images.
Okay, we're going to go to the Jet Propulsion Laboratory now. JPL, if you'd please state your name and affiliation before asking your question. Go ahead.
3 quick questions. One, you said you had some actual numbers on the sizes of the spot and the rings and the smudge. I wonder what those are. Can you nod up and down if you can hear me? Am I coming through now?
Yeah.
Okay. This is Robert Lee Holtz at the Los Angeles Times. You mentioned a moment ago that you had some actual numbers on the estimated sizes of the spot and the ring and the smudge. I wonder if we could hear those numbers, and then I have 2 quick follow-ups.
All right, these are very, very preliminary. We haven't had much time to do detailed analysis. For our first cut analysis, the diameter of the black ring, and if you show the blow-up version, they'll have a better idea of what I'm talking about, or the white ring if you have a methane image available. The diameter of that sharp, thin ring is about 7,500 kilometers, and the diameter of the white ring surrounding that, the inside of the black eye, as it were, that's about 15,450 kilometers.
Are there any other questions from JPL?
Yes, just 2 quick follow-ups. I wonder, and perhaps this is for Gene Shoemaker, if you could compare, in your mind, the size and energy of this fragment to the object that is believed to have caused the Chicxulub crater.
Okay, the minimum size of the Chicxulub crater, and it's still a matter of controversy, the full crater, I prefer to use the minimum value, which is about 180 kilometers in diameter. So we're talking about something that's 3 times smaller, and the energy here then is 27, roughly, about 27 times less. So this is This is a big event, but it still isn't the dinosaur killer.
Do we have any more questions from JPL?
For us, the level of internet and email traffic that you're seeing. How crowded is the electronic huddle?
Well, we have an email distribution network set up for the professional astronomy community, and that is actually working extraordinarily well. People are being very concise about reporting their observations, and therefore we have, in our parlance, very high signal to noise. A very good amount of information is coming through. When I saw there this morning that one of the images from the IRTF showing the G impact plume was posted on one of the Mosaic bulletin boards, I tried to connect, and I could not get through. And they said that there was so much traffic on the networks trying to reach some of these very popular sites that you know, things are getting, there's a big traffic jam on the information superhighway right now. But this is an extraordinary event. I think that's why. Normally we don't have that kind of difficulty.
Are there any more questions from
This is
JPL?
Dan Blackburn, KCOP TV in Los Angeles. Are you getting any readings yet that tell you the depth to which these impacts are going, or does it look pretty much as though it's staying very high in the atmosphere of Jupiter?
I don't think we have a good answer for that question yet. We're working on that kind of a question. You know, we know something more about the heights because we can see them sticking away from Jupiter. It's awfully hard to know about probing deep. One thing that will tell us for sure is some spectroscopy that's being planned by many telescopes around the world, including the IRTF, including the Kuiper Airborne Observatory, and many others, looking for water, the signature of water. If we see that, then we will know how far, at least that particular explosion went, how far deep that impacting body went, because we hypothesized the level at which the water clouds reside. We can't see it. It's below the visible cloud deck. So that'll be a clue as to the depth. It could be, too, that from these images we might be able to pull out some of this information. That's going to take some very clever thinking on our part and on the part of the modelers to pull this all together and make a coherent story. I think we're still far too premature to be able to answer it with any certainty.
Walter Richards of KTLA Los Angeles. I have two questions. Would anything be left of Jupiter once this is all over? And what impact would the impact be on Los Angeles if it were hit the same way?
I think Jupiter's going to hang in there. It's a pretty big planet, and we're seeing these big splotches and black eyes and bruises. I feel sorry for Jupiter. It's really getting pummeled. But I think it's going to hang in there, and the bruises will fade after some period of time, which we don't know yet. I'll turn the Los Angeles question over to Gene.
That being my native hometown. Well, if this 60-kilometer crater is the right estimate, I think it's pretty good. And you put a bullseye over City Hall in Los Angeles, that's going to take out everything in the crater. It'll take out all of LA County, and in fact, I just wouldn't want to be in Southern California, period.
Okay, if there are no more questions from JPL, we'll go to Marshall Space Flight Center. Once again, please state your name and affiliation before asking your question.
This is Masahiro Takemura, a science writer for a Japanese newspaper, the Yomiuri Shimbun. I have questions about the impact energy of fragments. As far as I understand that the impact energy is proportional to the cubic radius of a fragment when the impact velocity is the same. Is it all right?
Yes, that's right. The impact energy is proportional to the cube of the radius and to the square of the velocity.
Do you have the estimated figure of energy in terms of TNT, which is caused by the impacts of all the fragments of the SL9?
Well, you could start to add them up. We've seen perhaps the biggest. I'd multiply that by a factor of maybe 6 to 8 might give us the total, somewhere in that ballpark. So we're talking about something of the order of 40 million megatons, perhaps, of energy. Very rough ballpark. Give that a slosh of at least a factor of 10 million megatons either way or more, because we're just going on what we've seen so far.
Okay, we're going to leave Marshall and come back here to Goddard to take any more questions over here.
It's kind of an elementary school question, but since Jupiter is so much more massive than Earth, and gravity is pulling these guys in, therefore it's got a stronger gravity, wouldn't a comparable mass hit Jupiter with greater velocity and therefore energy than it would Earth?
If I understand your question, is if you have the same mass, one's falling in Jupiter and one's falling on Earth, would it have more energy? Is that the question?
Would it have more energy on Jupiter because Jupiter has a larger mass and therefore it can create
Exactly. Jupiter is accelerating these objects as they come in. And in fact, the velocity with which these fragments are hitting Jupiter essentially is the escape velocity from Jupiter. And that's 60 kilometers per second, whereas if you had an object that just fell in at the escape velocity on the Earth, that's only 11.2 kilometers per second, and the energy is going as the square of the difference. So it's a factor of 5.5 or something like that. Square it. So there's a factor of difference of 30 in the energy that you would get if just something just falls in at the escape velocity.
This is Mark Carreau of the Houston Chronicle. I think I appreciate how optimally the planet was turned to get this picture, but I'm just curious, if this impact had happened sooner, would it have been on the far side and you would have missed it? Is there any kind of a timing you can give us as to how lucky you were to capture this thing?
Well, the impacts are always occurring on the far side. Timing is irrelevant because they're coming in on a line that always is the same orientation relative for us and Jupiter. So it wouldn't matter if it came in early or late. We would never be able to see it. In terms of the timing of the imaging that we took, that for our program was really limited by the rotation of the Hubble Space Telescope's orbit around the Earth. It orbits every 96 minutes, and obviously we can only look at it at Jupiter when the Space Telescope is on the side of the Earth that Jupiter is visible. We can't look through the Earth. So in some sense, we have been extremely lucky to have captured 3 of these impact events in the middle of one of the Hubble's visibility windows. And it's almost by definition, if that impact plume is visible, then 1.5 hours later, we'll be able to take a picture of the site just on the disk of the planet, because that's how fast Jupiter rotates. So we were fortunate to have the Hubble in the right place at the right time to be able to capture this one. We couldn't have done anything if the Hubble had been on the other side of the Earth.
I think part of the answer to the question, Heidi, is that we already had very good predictions of the impact times. They were certainly good to within 15 minutes.
Right.
And so that was extraordinarily important in the timing, in the planning for these images. That was a very essential part of your planning.
Well, not really, Gene.
No?
Because we had to do the planning and the sequences many weeks ago, months ago, and the impact times were not well known. And the Hubble's orbit was not particularly well known either, because that has to be adjusted fairly frequently. And so, in some sense, it was pot luck. And as the predicts were coming in and changing forward, backwards, they would be hopping in and out of orbits, and I'd be getting very nervous, and then I'd be very happy, and then I'd be nervous again. And so I ended up being very happy.
Yeah. But you certainly were doing your initial planning based on the Chodos and Yeoman's predicts.
That's right, but there were big uncertainties.
But there was a lot of luck that it came out the way.
There's a lot of luck. We've been very fortunate.
Yeah.
Got a question in the middle, right over here.
Tracy Watson, U.S. News and World Report. First of all, I'd heard that looking at the plume may indicate sometime what the composition of the impactors was and will eventually tell us whether it really was a comet or whether it was an asteroid. How long do you think it'll take you to come out with that kind of information?
I'm not sure we'll get that information from the plume itself, although we'll have to think about that for a while. I think it's more likely that kind of information is going to come from spectroscopy of the impact sites, the fresh impact sites. And that work will be done with a variety of instruments. Hubble is one of them. In fact, we had a very exciting exercise this morning where we got that first image that I showed you of the impact site on the limb, and in real time we measured exactly where the Space Telescope was pointing and then offset the telescope to be pointing exactly at the impact site and sent the instructions up to the spacecraft. Normally we don't do that. We plan weeks and months in advance. And Keith Noel is the principal investigator of that experiment, and at some point in the near future I hope that he has some good results to share with you. Other telescopes like the IRTF and NASA's Kuiper Airborne Observatory will be instrumental in doing the kind of spectroscopy to probe the chemistry of the atmosphere and of, you know, any mushed up comet that happened to be there.
Bill Harwood, CBS again. I think I know the answer, but this is something that should be clearly visible to amateurs, is it not? I mean, given its size, or is the wavelength such that it's not going to be visible? Like which?
Well, these black spots are starting to get pretty darn big, and you know, close to the size of the Great Red Spot. And I believe there have been some reports from visual observers who are starting to see them. Now remember, you have a very high-resolution image in front of you with the Hubble Space Telescope. And with a ground-based telescope, much of this is smeared out. So it isn't anything like you're seeing here through a ground-based telescope. But the short answer is that, yes, this is starting to get large enough that amateurs may be able to spot these if they're very careful observers and know what to look for. And that three impact sequence may stir up a real big portion of atmosphere, may get very dark. It's also possible that with time, as the winds on Jupiter start to distribute this material, it's possible that a slightly darker band will develop in this latitudinal region. We say it's possible because, as I mentioned, this material appears to be very thinly deposited over that region. And so it's not clear if you start spreading out that thin layer whether or not there's enough there to make the band dark. We'll see that as it develops over the next week or two.
I think there's a good chance that amateurs with 8-inch diameter telescopes or bigger in good sites where they have very good seeing will be able to see these. I think that, and already there are reports from quite reliable observers.
There's a graphic we can show you that was shown this morning, which is the full disk of Jupiter and the 3 impact sites on the bottom, and I believe they have that they can put on. There it is. You can see the bands on Jupiter. This is roughly a visual image. This is a green wavelength, and that's more or less, you know, what you would see with your eye. And you can see the bands, and you can see the Great Red Spot, and you can see the little dark splotches following after the Great Red Spot. All right? So if you can see the Great Red Spot moving, it would start on the left of this image and move to the right. Then look further south for that little train of dark features, and you may see it.
All right, if there are no more questions, we'll wrap it up here. I want to thank everybody for their interest, and we'll see you. Okay, if people want to stay, we're going to roll some visuals up on the screen.
Good stuff. That's good. Good report, Type.
For more information about the NASA STI program, please write to the NASA Center for Aerospace Information or call us at 301-621-0390.